Welcome to our deep dive, everyone. Today we're taking a plunge into electroweak symmetry breaking and all that juicy physics beyond the standard model.
Sounds like someone sent in some fascinating stuff.
Oh, they did. We've got academic papers, lecture transcripts, even a perspective piece from Nature Physics.
Oh, wow, a real mix.
Yeah, perfect for a deep dive.
Mm-hmm.
So today's mission, we're going to extract those shiny nuggets of knowledge from all this material, give you a clear picture of what electroweak symmetry breaking is, why it's such a head-scratcher, and how those BSM theories try to solve it.
And maybe a few surprises along the way.
Oh, definitely. Like why that Higgs boson discovery might not be the end of the story.
The standard model's been a rock star, right? Explaining those fundamental forces like a champ. But
Yeah.
there are some gaps.
Yeah.
It can't explain everything.
Yeah, like where does gravity fit in? And what about dark matter and dark energy? Total silence from the standard model on those.
Exactly. And even within its comfort zone, what it does explain, there are puzzles.
Puzzles like.
Like the Higgs mechanism, how particles get their mass. That's a big one.
Okay, so let's rewind a bit. Remind me how the Higgs mechanism works and why that Higgs boson was such a celebrity.
Right. So the Higgs mechanism, it's all about this field that permeates everything, space.
Yeah?
The Higgs field, particles interact with it, and the strength of that interaction, boom, that's their mass.
So finding the Higgs boson was like proof this field actually exists.
Exactly. Like finding its fingerprint. Confirmed. It's not just some theoretical fantasy.
So a landmark discovery for sure.
Yeah.
But if it works so well, why are we still looking beyond the standard model?
Well, it's the Higgs boson's own mass that's the problem.
Mm-hmm.
The standard model doesn't predict it. And the mass, we did find 125 GeV.
Uh-oh.
Yeah, it leads to this thing we call a hierarchy problem.
Hierarchy problem. Two words I hear a lot but always get a bit fuzzy on. Can you break it down, like for a physics enthusiast who maybe skipped a few classes?
Okay, imagine a tiny boat on a stormy sea. The boat is the Higgs mass and that stormy sea. Those are the quantum corrections, virtual particles popping in and out of existence. They should be pushing the Higgs mass way up, like a monster wave capsizing our little boat.
So the question is, how does the Higgs mass stay so small? How does our boat survive?
Exactly. The standard model has no answer. It just doesn't explain why the Higgs mass isn't swept away to some crazy high-energy scale. It feels unnatural.
Like the universe is playing this balancing act with the Higgs mass, and physicists are like, wait a minute, this is way too precarious.
Yeah. This fine-tuning problem, it screams, there's something deeper going on. Something beyond the standard model that explains why the Higgs mass is so stable.
You mentioned something about a minus sign, too, adding to the mystery.
Right. Another sign the standard model story is incomplete. To make spontaneous symmetry breaking happen, which is crucial for the Higgs mechanism, we need to stick a negative term in the Higgs potential equation. But there's no fundamental reason for it. It's just a trick to make the math work.
So we're kind of forcing the equation to fit what we see, not really understanding why it should be that way.
Exactly. That arbitrary minus sign is another clue. It's a deeper truth out there.
So we've got this hierarchy problem, the minus sign mystery, and the standard model's looking a bit shaky. I know there are all these theories beyond the standard model trying to fill in the blanks. Where do we even begin?
Well, a lot of these theories, they have a common thread. Symmetry. Introducing new symmetries into the standard model might be the key to taming those wild quantum corrections and stabilizing that Higgs mass.
Symmetry as a solution. I've seen supersymmetry, or SUSY, pop up a lot in these sources.
Yeah.
Is that the leading contender?
Oh, it's definitely a strong contender.
Yeah.
Very elegant. It's based on this idea of a fundamental symmetry between fermions, the matter particles, and bosons, the force carriers.
Okay, I get the fermion boson thing, but how does that help with the hierarchy problem? Explain it like I'm 5, but maybe a 5-year-old who's already aced their intro to physics?
All right, picture a seesaw, perfectly balanced. You've got a heavy weight on one side that's those pesky quantum corrections pushing the Higgs mass up. SUSY comes along and introduces new particles, superpartners. They're like weights on the other side, perfectly counterbalancing and keeping the Higgs mass stable.
So CSY is like a cosmic balancing act, bringing in new players to keep the Higgs mass in check.
Exactly. Every standard model particle gets a superpartner with opposite spin. So for every fermion, a fermion, for every boson, a bosino, and they contribute to those quantum corrections, but with opposite signs canceling out the dangerous ones.
It's like they're each canceling out their partner's bad behavior, keeping the Higgs mass from going haywire. Pretty neat.
And it gets better. CSY doesn't just fix the hierarchy problem. It tackles other mysteries too, like unifying forces and explaining dark matter.
Okay, now you're talking. Unification of forces. Tell me more.
The standard model describes 3 forces right. Electromagnetism, the weak force, the strong force. But physicists have this hunch they might all be part of one unified force at super high energies.
You know, one of the sources actually has this graph showing how the strengths of these forces converge at high energies in SUSY, like separate rivers merging into one big, powerful stream.
Yeah. SUSY provides the framework for that unification, suggesting those forces are just different branches of the same tree.
Unification, a stable Higgs mass? What else is SUSY hiding up its sleeve?
Oh, it even offers a candidate for dark matter. You know, that mysterious stuff that makes up most of the universe but doesn't interact with light. The lightest supersymmetric particle, the neutrino, it fits the bill perfectly.
So SUSY solves the hierarchy problem, hints at force unification, and gives us a dark matter candidate. Talk about overachieving. But if it's so great, why haven't we found these super partners yet?
That's the million-dollar question. The LHC hasn't seen any direct evidence for them, which leads to what some call the little hierarchy problem.
Wait, a little hierarchy problem on top of the big one.
Basically, the Higgs mass we observe suggests some superpartners should be relatively light within the LHC's reach, but we're not seeing them.
So either SUSY is wrong, or there's a reason those superpartners are heavier than we expect. Is that where this LEP paradox comes in, the one mentioned in the natural physics piece?
Yes. The LEP, the collider before the LHC, didn't find any superpartners either. It puts constraints on those simple SUSY models, especially minimal supergravity, which predicted lighter superpartner masses.
So the LEP paradox is like, if SUSY's right, where are those particles hiding? Putting pressure on the theory to explain itself.
And to make it work, some SUSY models need some fine-tuning, which kind of defeats the elegance of the original idea. It seems we can't escape fine-tuning entirely.
So even SUSY, with all its bells and whistles, might not be the complete picture. Still lots to learn about this little hierarchy problem.
Absolutely. And that's why exploring other paths is crucial. Other BSM theories that could shine light on these puzzles.
And speaking of other paths, we've got a lot more ground to cover in this deep dive. Next up, that intriguing world of little Higgs models, where the Higgs gets a surprising makeover.
From fundamental particle to composite creation.
Stay tuned, folks. We're about to enter the realm of collective symmetry breaking and see how something little can tackle some of the biggest problems in physics. Welcome back to our Electro Week symmetry breaking adventure. We just explored supersymmetry, and now we're onto something called the little Higgs model. I gotta say, from what I'm seeing in these sources, it's a pretty out there approach.
You could say that. It actually takes inspiration from a surprising place, the world of pions and the strong nuclear force.
Wait, pions. Those things holding atomic nuclei together, how do they relate to the Higgs boson and the hierarchy problem?
That's where theoretical physicists get really creative. The basic idea is to think of the Higgs not as a fundamental particle by itself, but as a composite particle, kind of like a pion, arising from interactions of new, even more fundamental pieces.
So instead of a solo act, the Higgs is more like a band with different members contributing to the overall sound.
I like that analogy. And the cool part is how this idea tackles the hierarchy problem.
Okay, I'm all ears. How does a composite Higgs help with those pesky quantum corrections that were threatening to make its mass explode?
That's where collective symmetry breaking comes in. Instead of SUSY and superpartners, little Higgs models bring in a new set of particles and symmetries that work together to protect the Higgs mass from those destabilizing quantum corrections.
So it's like a team effort, a coordinated defense against those quantum bullies.
Exactly. And it's very similar to how pions get their mass through the strong force. It involves breaking something called chiral symmetry.
Chiral symmetry. Getting a bit technical now. Can you unpack that for me?
Sure. Think of it this way. You've got a left hand and a right hand. They're mirror images, right? That's a kind of symmetry.
I see where you're going with this.
Now, with particles, quarks come in different flavors, like up and down. And if those quark masses were zero, the strong force would treat left-handed and right-handed quarks as totally separate, perfectly symmetrical. That's chiral symmetry.
But quark masses aren't zero in reality, so is this chiral symmetry broken?
Exactly. Quarks having mass means left and right-handed ones can interact and transform into each other. That breaks the chiral symmetry.
Okay, broken chiral symmetry. So this is how the pion gets its mass.
You got it. The pion, which is made of quarks, acts as a messenger of this broken symmetry. It's what we call a pseudo-Goldstone boson.
Hold on, pseudo-Goldstone boson. You're going to have to explain that one.
So when continuous symmetry breaks, you usually get massless particles called Goldstone bosons. Think of them like ripples in space-time representing the lost symmetry directions. But sometimes the symmetry isn't completely broken, it's slightly tilted, hence pseudo-Goldstone.
So it's like a Goldstone boson that got a little lost along the way.
Haha, yeah, something like that. And because the symmetry breaking is only partial, these pseudo-Goldstone bosons aren't totally massless, but they're still super light. The pion's a perfect example.
So the pion's mass comes from this broken chiral symmetry, and its pseudo-Goldstone status protects it. And now we tie this back to the Higgs.
Precisely. Little Higgs models apply this same logic. We imagine the Higgs as a pseudo-Goldstone boson from the breaking of a new, bigger symmetry group. So its mass is shielded from those big quantum corrections and stays relatively light, even though it's not truly massless.
Okay, I think I'm getting the gist here. Composite Higgs, new symmetry group protection from quantum fluctuations. But what's this collective part in collective symmetry breaking? Why the team effort?
It's all about how these new symmetries are built. In little Higgs models, you need at least 2 interactions to fully break the symmetry and give the Higgs its mass. Remove one, and the symmetry is partially restored. The Higgs stays a pseudo-Goldstone boson light as a feather.
So it's like having 2 keys, and you need both to unlock the door to a heavy Higgs mass. One key missing, and the Higgs stays light.
Perfect analogy. And because you need 2 interactions, those nasty quantum corrections causing the hierarchy problem are suppressed. They appear at a higher order in perturbation theory, meaning they have a much smaller effect on the Higgs mass.
Pushing the problem further away to higher energies where it's less of a threat? So does this mean little Higgs models completely solve the hierarchy problem?
Not completely. It's more like giving the standard model a longer lifespan before the hierarchy problem catches up. Little Higgs models are still effective field theories. They only work up to a certain energy.
A temporary fix-a-bridge to a more fundamental theory that takes over at higher energies.
That's a good way to put it.
Yeah.
And that energy scale where little Higgs breaks down is around 10 to V. Much higher than the T-scale where the standard model starts having issues.
So we have UCY with its superpartners and little Higgs with its composite Higgs and collective symmetry breaking. Both tackle the hierarchy problem, but in different ways. Is one better?
It's not about better or worse. It's about understanding their strengths and weaknesses. SUSY is elegant, but faces the little hierarchy problem. No superpartners at the LHC. That needs some fine-tuning to make the theory agree with experiments.
And little Higgs? Any skeletons in its closet?
It has its own issues. It can also lead to some fine-tuning, especially in suppressing a term in the Higgs potential that's key for getting the right Higgs mass. It's a delicate balancing act.
So even with little Higgs, we might not completely escape fine-tuning.
Sadly, no. But that's science for you. We refine our theories, test them, and adjust course as needed.
Speaking of tests, we've talked about the hierarchy problem and the minus sign puzzle. But what about experimental predictions? Does little Higgs offer any testable signatures that could set it apart from Series Y or other BSM scenarios?
Excellent question. And this is where things get really interesting. Little Higgs models predict new particles around the TeV scale, just like Series Y. But these particles would have different properties interact differently, leading to distinct experimental signatures.
So if we see new particles at the LHC, but they don't quite look like SUSY particles, that could be a hint of little Higgs.
Exactly. And some little Higgs models, especially those with T-parity, can also predict a stable, weakly interacting particle that could be dark matter.
So little Higgs could explain dark matter too, like SUSY.
Yes, but the properties of this little Higgs dark matter would be different from the SUSY neutrino. So by studying dark matter experiments carefully, we might be able to tell them apart.
It's like having a cosmic fingerprint scanner searching for those telltale signs of new physics.
I like that. And as we dive deeper into BSM physics, we encounter even more radical ideas.
You've got me hooked. What else is out there beyond SUSY and little Higgs?
There's a realm where the Higgs boson itself might be a mirage, a reflection of something deeper and more fundamental.
A mirage. Now you're really blowing my mind.
Get ready to enter the mind-bending world of extra dimensions and gauge Higgs unification.
Okay, bring on the extra dimensions. I'm ready for anything. Okay, so we've journeyed through supersymmetry, explored that composite Higgs idea from little Higgs models, and now we're stepping into extra dimensions. I gotta admit, the idea of hidden dimensions beyond our 3D world is both fascinating and kind of intimidating.
It's definitely captured the imaginations of physicists for a while now, and it turns out they might be the key to cracking this electroweak symmetry breaking thing in a whole new way.
Okay, I'm ready to be mind blown. But first, why are extra dimensions even on the table in physics? It sounds like science fiction.
Well, it sounds like science fiction, but the idea's been around for over a century. Think Kaluza and Klein back in the early 1900s. They were already playing with extra dimensions, trying to unify gravity and electromagnetism.
So it started with unifying forces. But how did extra dimensions get linked to the Higgs boson and electroweak symmetry breaking?
That's where gauge-Higgs unification comes in.
Hmm.
Instead of the Higgs being a fundamental particle all on its own, we think of it as part of a higher dimensional gauge field.
Hold up, gauge fields. I know we've talked about them, but a quick refresher would be great.
Think of them as the carriers of those fundamental forces. The photon, for example, that's a gauge field for electromagnetism.
Hmm.
In gauge-Higgs unification, the Higgs actually comes from a gauge field that lives in a higher dimensional space, with extra dimensions beyond our usual 3.
So the Higgs is like a hidden part of a force-carrying particle only showing up in our 4D world. Mind-bending stuff.
It is, and it's a really elegant way to tackle that hierarchy problem. Because in this higher dimensional space, the gauge symmetry protects the Higgs mass from those big quantum corrections. But to bring it back to our universe, we have to compactify those extra dimensions, curl them up into tiny, unobservable sizes.
So we shrink those extra dimensions, make them invisible, but their effect is still felt in our 4D world.
Exactly. And because of that compactification, the Higgs appears in our world with a mass protected by that higher dimensional symmetry.
Like a cosmic safe house for the Higgs, keeping it safe from those energy explosions.
Love that analogy. Now, to really see how this compactification works, we've got to get a little technical. Your sources mention a 5-dimensional model where the extra dimensions is curled up in a circle. And the way you set boundary conditions on this circle determines how the symmetry breaks and how the Higgs gets its mass.
Boundary conditions on a circle. Sounds like some kind of cosmic game with rules that determine the outcome.
Not quite ring toss, but you're getting the idea. It's called orbital folding. This technique of setting boundary conditions on the extra dimension. And by choosing specific conditions, we can break the original symmetry in a way that gives mass to the Higgs and other particles.
Orbital folding. That sounds like something out of a fantasy novel, but it's actually a mathematical tool for shaping those extra dimensions.
Exactly. It's how we control how that higher dimensional theory shows up in our 4D world. And to understand how the Higgs mass is set in this scenario, we need to talk about the Hosotani mechanism.
Hosotani mechanism. I've seen that name pop up. Break it down for me.
Basically, it says the Higgs mass is connected to the size of that compactified extra dimension, smaller dimension, bigger Higgs mass.
So the size of a hidden dimension determines the mass of a particle we can see. It's like saying the size of a room determines how much the furniture weighs.
Might sound strange, but that's physics for you. Unexpected connections. But like any theory, gauge-Higgs unification has its challenges.
I bet. Getting it to match all those experimental measurements, those precise particle masses and interaction strengths, that can't be easy.
Yeah, it's tough to get to the right top quark mass, Higgs mass, and compactification scale all at once. And then there's generating that hierarchy of Yukawa couplings, which determine the fermion masses.
Elegant idea, but the devil's in the details. Like having a beautiful blueprint, but then realizing you don't have the right materials to build it.
Perfect analogy. People working on more realistic gauge-Higgs unification models. Some even involve breaking that 5-dimensional Lorentz symmetry. But it's still a work in progress.
So extra dimensions offer a framework for seeing the Higgs as part of this higher dimensional gauge field. But then there's Higgsless models I read about. That just sounds like a contradiction. How can you have electroweak symmetry breaking without a Higgs?
Higgsless models definitely go against the grain.
Mm-hmm.
They say electroweak symmetry breaking happens not because of a scalar field like the Higgs field, but from carefully chosen boundary conditions in those extra dimensions.
Boundary conditions again. They seem to be the stars of these extra dimensional theories.
You said it. In Higgsless models, these conditions are applied to the gauge fields themselves, which actually lowers the rank of the gauge group.
Wait, rank of the gauge group, that's a new one.
Think of it as the number of force-carrying particles for that force. In the standard model, the electroweak force has a rank of 4, the W+, WZ, and photon.
Okay, so in Higgsless models, something happens in the extra dimensions that reduces the number of force-carrying particles, like they're being trimmed away by these boundary conditions.
Great visualization. And by getting rid of some of those force carriers, you get electroweak symmetry breaking without needing a physical Higgs boson.
But doesn't removing the Higgs cause other problems, like unitarity violation? We talked about how the Higgs is crucial for keeping those scattering amplitudes from going crazy at high energies.
Excellent point. Without the Higgs, the standard model would violate unitarity around the Taft-Gazel. But in Higgsless models, something else steps in. Kaluza-Klein states, more new particles to add to the mix. This is getting complicated. Think of them as heavier versions of the particles we know, coming from the quantization of momentum. in those compactified extra dimensions. These KK states get involved in interactions and help with those scattering amplitudes, delaying the energy growth and restoring unitarity up to higher energies.
So a backup team of particles keeps the theory from falling apart.
Exactly. But even with this clever trick, Higgsless models have their issues. They struggle to explain certain precise measurements of electroweak interactions.
Those experimental constraints always popping up to challenge our theories.
Right. And to make Higgsless models work with these measurements, you often need warped extra dimensions, where the geometry of the extra dimension isn't flat but curved. This warping can help make things agree with the data.
So Higgsless models, while interesting, still have some work to do. Finding a BSM theory that ticks all the boxes: theoretical consistency, experimental agreement, and a good explanation for electroweak symmetry breaking. It's a tall order.
It is. It's a massive puzzle, and we're still hunting for those missing pieces to complete the picture.
Well, this deep dive has been quite a ride. We've gone through supersymmetry, little Higgs, extra dimensions, each with its own approach to electroweak symmetry breaking.
We've seen how important symmetry is, how the hierarchy problem pushes us to find new physics, and even how we can have electroweak symmetry breaking without a Higgs in some theories.
It's amazing how creative and persistent theoretical physicists are always pushing the boundaries.
It's that drive to explore that fuels scientific progress. And who knows, maybe the answers are already hidden in the data we've collected, just waiting for someone to see them in a new light.
We've given you plenty to think about, and we've included links to all those sources you sent in so you can keep exploring. Thanks for joining us on this deep dive into the world of electroweak symmetry breaking.